So, hi everyone. Today we have Jibin Joseph. We will be giving a talk about the numerical viscosity in protoplanetary disk, and in particular in Cartesian simulation. Jibin Joseph, who is from Potsdam. So please go ahead.
Yes, thank you very much. It's really a pleasure to be invited to give this talk on my recent work. So this is a project I did when I was a master's student at the University of Tübingen. Up to earlier this year in March, I was a student there. And the research is about measuring numerical viscosity in disk simulations using the viscously spreading ring problem. So I'd like to just get started with it. So there are two parts to this talk, also to the paper. In the first part, we talk about the viscous spreading ring problem. In 1D, in 2D, and in 2D, you would have the viscous spreading ring instability. And we'll compare it to a previous study on the same. And in the second part, we'll use the viscous spreading ring to actually measure the numerical viscosity. Yeah, so what's the viscous spreading ring? There's a good introduction in the paper by Lyndon Bell and Pringle, 1974, one of the classics. I think the oldest reference we found was by Lust, 1952, so it can be pretty old. But if someone wants to read, can refer to this paper. So the idea is the following. So you start with initial density distribution of, so ring-like distribution of a mass M ring at a radius R0, so it's a delta function. And you plug it into the vertically integrated hydrodynamics equations. And you make some assumptions, like the fluid is pressureless and the kinematic viscosity is much less than the specific angular momentum. And you will get an approximate solution, analytical solution for the time evolution of the density distribution and the radial velocity. So you see UR ring and sigma ring. And I would like to bring your attention to this equation here, sigma ring, which depends on a bunch of constants. And the distribution then depends on the factor tau here. So you have some Bessel function, you have some exponential function. In the end, they depend on x and tau. So x is the distribution and tau is at a given normalized time. And if you notice, the equation for the normalized time is a linear function of viscosity. So the ring spreading scales with the viscosity. So if you have more viscosity, you would reach a further state in the ring spreading at a given time t. So if t is in units of orbital times, let's say, your tau will scale with viscosity. And then you have a normalized distance, which is just, a normalized distance. So on the left, you can see this ring spreading in action. So this is taken from a paper by Willy Clay in 1998. So you start with an initial distribution and the ring spread. So the solid line is from the analytical solution, and the crosses and the triangles and the boxes are from the simulation. And you can see that they match pretty well. So you start with an initial condition. You don't start with the delta function because it's hard to do that on a simulation. You start with some tau and you let the ring spread and you get the ring spread. I suppose a lot of people here know about this. It's a very classic problem. It becomes interesting when Roland Speight and Willy Clay looked at this in 2D. So in that paper, they had two parts. The first part was the theoretical part, where they looked at the viscous spreading ring and the stability of the string in 2D. And they came up with a dispersion relation given an initial perturbation. And they found that this initial perturbation will be unstable if you have perturbations with wave numbers that are larger than a certain criteria. So you need to satisfy a certain criteria. And then if you have those perturbations will grow, be unstable and grow and develop a spiral-like structure. And so in terms of simulations, that would mean that if you're simulating this viscous spreading ring on a grid, you would need to be, the grid should be able to resolve these small wavelengths that need to suffice this condition. And they tested out with two codes. So they used an SPH code, and then Willy also added his RH2D code, which was a finite difference code. and they both saw the same result. So you seed the viscous spreading ring with a perturbation, and the perturbation grows, and you develop this spiral arm structure. But what they saw was that you form this flip in the spiral arm. So you have this inner spiral region where you have a trailing spiral, and the outer region, which is like a leading spiral. And this is what was also shown with the finite difference code. So here you're seeing the SPH results, and the other one I've not shown here, but is also confirmed with the finite difference code. So as an initial step, what we wanted to do was test this viscous spreading ring and recreate the results, both in 1D and 2D. And for that, we used the PLUTO code. So the PLUTO code is a finite volume code, and we implemented a second order scheme using a linear reconstruction with a HLLC Riemann solver and a Fourier flux limiter. So stuff that is pretty standard for protoplanetary disks, so not very expensive, also sufficiently accurate and robust. Then for our physical setup, we had a central star with a potential, so just a single star in the center, and a locally isothermal prescription, so with a disk aspect ratio of 0.005. So we went with this low value because we wanted to recreate the conditions that are necessary. So very low pressure, but we could also not go with zero pressure because the simulation is just not working then. So we went as low as we could to find a good balance between low enough pressure, but simulation robust enough. So we first implement this on a polar grid. So to start with, and for a polar grid in 2D, we use the FARGO scheme, so the advection scheme. We also tested it without the FARGO scheme. It was just slower. Of course, the FARGO scheme gave us an advantage, so we just kept it. We used the logarithmic grid to get the high inner resolution in the inner region, sorry. And for a fiducial resolution, we used 465 by 256. So keen eye would notice that this is not square cells, but we would come to that later. And in the inner region, we use a strict outflow boundary condition. So that means that anything that is going out will go out, but nothing is reflected back in. So anything that's trying to reflect back in would be forced to go out. Yeah, so here you see the results from the 2D run on the right side. What you're seeing here is the density deviation from the ring solution. So sigma minus sigma ring normalized to sigma ring, so that we can catch any small deviations. So on the left panel here, panel A, it's just after the simulation starts, you see this wave going through the domain. So it's R along the y-axis and phi along the x direction, let's say. And these are rings, these are not spirals. So a ring-like wave goes through. We think it has to do with the viscous overstability, but it's not within the scope of this work, so we didn't go into it much later. But more importantly, once this initial wave goes through, you develop the instability pretty soon in the inner region. So you can see this ring-like structure. It's growing, and in C and D, you can see that it grows and sort of saturates. So you have this one spiral arm structure that grows and develops and saturates, covers the entire domain. So this was kind of good, but also confusing for us because we could not exactly reproduce what Roland Speight and Willy Clyde showed in this paper. So we didn't get the flip in the spiral. So we didn't know what was exactly happening. So we did a resolution study. And we also collaborated with Lucas Jordan, who used this FARGO code, which is also a finite difference code, so more similar to the RS2D code, to see what was happening. And when we did our resolution study, we looked at the growth rates. So that's what is shown in the right panel here. We are looking at the growth rates as time goes by. And you can see that our fiducial resolution, which is in green here, is sufficiently good in the sense that if we increase the resolution, we don't see significant differences. But if we go lower in resolution, we find that the instability is not completely developed. So there is some sort of let's say dampening of the growth. And in particular, you can recreate that flipped structure if you go to a lower resolution, which is what was used in Willy Klei's paper or Ulrich Klei's paper. On the right, what you see is what happens if you use a square cell, so a cell aspect ratio of 1, compared to what we used, and we saw that it does not really make a difference, and the majority of the difference comes from the radial resolution. It's more sensitive to that, so we just crank our phi resolution down so that we can get things done faster. What we noticed was that you don't develop the double spiral structure, or let's say the spiral flip, but you develop the single spiral structure, and we confirmed this with the FARGO code as well. But that's a different thing, and now we use this on a Cartesian grid. We wanted to see how the viscous spreading ring behaves on a Cartesian grid. So we wanted to create an equivalent setup on a Cartesian grid. So we use exactly the same sort of setup and methods. But now we have a Cartesian grid, and for our fiducial resolution, we used 1024 squared, because that gave sort of 1 CPS at R0 that we were interested in. And for our boundary condition, we used outflow on the outer regions. But more importantly, on the inner region, we wanted to recreate the polar cutout in the center. So we used a damping region for R less than 0.2 R0, exactly like the polar grid. For our standard runs, so the runs with which we just test the viscous spreading ring, so you have some viscosity that you have prescribed in the simulation. We damp the solution in this inner damping region to sigma ring. So we just damped it to the analytical solution. So we forced it to the analytical solution. And for inviscid runs, we didn't do that, of course, because I'll come to that later, but we damped it to a sigma floor value, a density, a floor value for the density. So what do we see? So on the right here, you see results from the 2D Cartesian simulations, and what I'm showing here is just a slice, so along the y equals to 0 line or the x-axis. And you can, the solid line is from the simulations, and the dotted lines is from the analytical solution, and you can see that it matches pretty well. We looked at the errors, it was sufficiently small, although larger for the radial velocity, which is on the right side. It's still pretty good. So in most of the domain, it does the spreading pretty fine. It's good. But what you do not see are oscillations on this spreading ring. So if you have the instability developing, you would see variations on this ring, but you don't see that. We looked at it in 2D picture as well, of course, but we don't see the instability develop. So we thought the resolution was not enough, so we cranked up the resolution. We went up to 2048 squared, and we still didn't see the instability develop. So we think this had to do with the numerical viscosity and the grid effect of Cartesian grids. But to also eliminate that this has nothing to do with the damping region, we tested the different damping regions and moving them in and out and so on and so forth. But it does not really make a difference. So we narrowed it down to grid effects. So now we have the viscous spreading ring in 2D, and the 1D comes out of it. And now we want to use this to measure the numerical viscosity in Cartesian grids. But before I go into this, I would like to motivate a little bit, why do we need to constrain numerical viscosity as a value? Because we know that there's numerical diffusion in a grid. We know that grid solutions make errors. But why do we need to exactly constrain a value? So I've been told that most of us here do simulations, accretion disk simulations. And we know that simulations work by discretizing the hydrodynamics equations, at least hydrodynamics equations work like that. And this discretization inherently introduces errors. Part of one of these errors being numerical diffusion, numerical dispersion being one of the other ones. And this diffusion may act like effective numerical viscosity. So we don't know yet, we'll look into it, but it may. There are multiple ways that we deal with this, right? So as a computational astrophysicist, you would want to reduce this error. And the simplest way, or in terms of implementation, at least, is you just crank up the resolution, right? Or you just increase the resolution and try to find some sort of convergence. But sometimes it's not possible. So use something advanced like a higher order method or some kind of a solver that's less diffusive. Or if you're lucky, you can use a problem specific setting. But the choice is usually between finding a balance between computational cost, robustness, and accuracy. So as a computational physicist, you want to get your results as fast as possible and as good as possible, but also make sure that you want to have those results. So it should be robust. But if you're working on something like accretion disks, you're kind of lucky because you can use a spherical polar grid, or in 2D, you can use a polar grid because the polar grid matches very well with the geometry of an accretion disk. So in an accretion disk, you have flow that is mostly along the azimuthal direction. So the majority of the flow is along the azimuthal direction, and the polar grid does that very well. So you can fit your accretion disk on a polar grid, voila, perfect. But that's how good as it gets, right? So if you want to include the center of an accretion disk for some reason, let's say if you're simulating a binary system and you want to actually simulate the flow onto the binary components, polar grids are hard to do because you can't go all the way to the center, and the closer you go, the more you're constrained by your time step and so on. So you usually make a cutout, or you just use a Cartesian grid, at least if you're using a grid-based method. But even if you're not doing that, if you have some sort of a planet in your disk, right? So you just have your disk, but you have a planet in your disk. Locally around the planet, you're still having flows that don't align with the polar grid. So you're sort of having a Cartesian geometry around the planet. So considering this, it is kind of important that you know how much numerical viscosity there is in these situations. And if you're using Cartesian grids to avoid these problems, then it is good because it works. It does not stick to a certain geometry, but then it creates high numerical diffusion. So then it's good that you can have some sort of constraint, especially if you're measuring accretion rates, let's say onto a binary component. You want to know how much of that contribution is due to numerical diffusion from the grid. So how do we do that? It's rather pretty simple. It comes back to that equation on the first slide that I showed you, the sigma ring equation. It depends on tau, the distribution, and tau depends on viscosity. So if you have viscosity in your simulation, the ring will evolve. And the idea is to let the ring evolve on a grid without prescribing any viscosity. So you don't prescribe any viscosity, you set viscosity equal to 0, and you put it on a grid. In principle, the ring should not spread, right? Because the evolution should just be constant, it should not move. But if the ring evolves, that means there is some sort of an effective viscosity that is acting on it, and it makes the ring spread. In principle, the ring can spread in any way it wants. It does not have to spread in the normal fashion that comes from the analytical solution. But assuming that it does, you can fit it to the analytical solution and extract a numerical viscosity back from the simulation. And that's exactly the idea. So just to reiterate, you start with a simulation which has no viscosity, no prescribed viscosity. You implement this viscous spreading ring. You let the ring evolve. You hope that the ring spreads like the analytical solution. You fit the analytical solution and you reverse engineer the numerical viscosity, basically. And that is what we did. So we let the ring evolve on an inverted Cartesian grid, and we fit it with the analytical solution, and we extract it back. So how does this numerical viscosity play a role in your normal simulation, right? So in a normal simulation, you have some sort of viscosity. How does numerical viscosity affect a simulation with some prescribed physical viscosity? So that is what we wanted to test. So we did 2 more models. So on the right, you see a plot, and the blue line here, both the blue lines. So let's focus on the solid line first, solid lines on the top. So the solid blue line is from the inviscid model. So you have 0 prescribed viscosity. We let the model evolve. We fit the analytical solution. We extract the numerical viscosity. We feed this numerical viscosity back into the same setup, and we let the ring evolve again. So if now the grid has its inherent numerical viscosity plus a physical viscosity that we set to be equal to this estimated inherent numerical viscosity, you would expect the ring to diffuse or spread twice as fast, because the spreading is linearly related to the viscosity. So twice the viscosity, it spreads twice as fast. Or if you have twice the viscosity, you can get the same result in half the time. And that is exactly what we look here. So the blue, orange, and green curve. So for the green curve, we went a step further. We fed it 2 times the numerical viscosity. And we expect it to evolve thrice as fast. So we looked at it in 1/3 of the time. And we saw that it matches very well, except for some deviations in the top, which where gradients are very strong. And we looked at it for 2 different times in the simulation, quite far apart. So at t equals to 224 orbital times and 748 orbital times. And we saw that this relation, this linear relation is maintained. So what this suggests us is that the numerical viscosity in the simulation is just simply adding on to the physical viscosity, at least in terms of ring spreading. It's adding on to the physical viscosity. So your total viscosity in your simulation would be the prescribed physical viscosity and the numerical viscosity in terms of large-scale diffusion. So here I would like to show the actual values that we got for the numerical viscosity. So this 1024 squared model was our fiducial model. And we converted it to an alpha value in your disk, because people are usually generally interested in the alpha value. And for a protoplanetary disk, the general aspect ratio is 0.05. And if you use that value, you get an alpha of 10 to the minus 4. Yeah, 1.7 times 10 to the minus 4, which is, I think, significant enough. So it's something that you should keep a note on, especially if you're doing simulations where you're simulating winds and you want to get an effective alpha in your disk. This is something you should keep track of. Or if you're doing some sort of external accretion on the disk and you want to measure the effective alpha in your simulation, particularly if you're using a Cartesian grid, then you should keep this in mind. And we find a scaling of delta x squared, which is sort of what you expect if you have a second order accurate scale. We also corroborated this with results by collaborators that use the Athena++ code, and they found a similar scaling. We don't know why Athena++ is doing tiny little bit bad here, but it's pretty close. And the scaling is roughly delta x squared. We also checked what happens if you have the resolution in the x direction not the same as in the y direction. So we did a study with 5 and 12 times 1024, and we found that the numerical viscosity from that is more close to 5 and 12 squared. So it sits somewhere in between, but it's more skewed towards the 5 and 12 squared result, suggesting a relation of this sort. So a max of the cell size. So that was how we measured the numerical viscosity on a grid. But now we come back to what happened in the Cartesian grid, right? So we did the viscous spreading ring, not the inviscid one, the standard one on a Cartesian grid, and we saw that the ring spreading works pretty fine, but the instability does not develop. So we were like, what is happening there? So what we looked at is the growth rate of the instability. And on the plot here, you see this. So the solid line is in the Cartesian simulation, the fiducial Cartesian 1024 squared. And the dotted lines are from the polar simulation for 465 by 256. And what you see is that the polar one grows just like the previous plot, and it saturates to a certain level. But for the Cartesian grid, you can see that it just washes it away. So whatever perturbation, initial seed perturbation you had, it just washes it away, and it just kind of makes everything uniform, and it just saturates down to around 10 to the minus 4, which is 6 orders of magnitude weaker than what you get from the polar one. So it's really killing the instability off. We think this has to do with the high numerical diffusion that you have on this smaller grid scale, and also due to the lack of angular momentum that is a result of this, which just diffuses away whatever small modes you need to grow this instability from the criterion that I mentioned at the beginning. What this tells us is that in terms of the spreading of the ring, both physical viscosity and numerical viscosity can play a sort of similar role. So you can have numerical viscosity get you the same kind of result that you get from the physical viscosity in terms of ring spreading, but it can't play that role that is necessary. So physical viscosity here is necessary to develop the instability, but numerical viscosity can't do that. So numerical viscosity just diffuses away those features, and it can't work like physical viscosity, at least in terms of growing the instability. Yeah, so that's it. That brings to my conclusion. So we started by looking at the viscous ring problem, and we found that the viscous ring is unstable in 2D, and in fact just develops a single spiral arm. We confirmed that with the convergence resolution study, and we showed that the previous study was just under resolving the instability. We also found that if you do it on a Cartesian grid, the ring spreading works pretty fine, but the instability is not developing. And we went to a resolution as high as 2048 squared. We did not see it. And we think it has to do with the inherent numerical viscosity and also the lack of angular momentum conservation in those grids. Overall, we think we have presented a method which is decent enough, and it can give you the numerical viscosity in your simulations to a good accuracy. And we showed that this forms a good test for your code, right? So the viscous spreading ring as well as the instability. So if you want to test your code, you need to, it would be a good test to see that the viscous spreading ring is working good for whatever solvers and whatever method you're using, and also if the instability properly develops and saturates as a single spiral structure. Yeah, thank you very much.